Hello everybody, this is the fifth video in a series of videos on Python programming for engineers. My name is Mark Bakker and I work at the Delft University of Technology. Today we'll deal with two topics. The first one is how to fit a polynomial through a set of data. And the second topic is how to use the function fsolve to find the zero of a function. We'll start with polynomial fitting. What you see here on the screen is an array of x and an array of y values. Let's show them. Plot x, y, and I want to see blue dots in a line. This is the data. Oh, no line. Let's add the line. And you see that these data looks kind of like a polynomial, maybe like a third order polynomial. I'm not quite sure. How many data points do we have? Print the length of x to the screen. We have 8 points. To fit a polynomial through the data, there is a function called polyfit. Polyfit. We open the parenthesis and see what help we get. It tells us that it does a fit of a polynomial that looks something like this, where you can specify x and y and the degree of the polynomial and some other keyword arguments that we don't need to specify. So let's see, if we specify here x and y, those are the x and y values we have, and we have 8 data points. So if you want to go exactly through those data points, we need a polynomial of degree 7. Right? The polynomial of degree 7 means the highest power is power 7, but there is also a power 0. So we have 8 parameters to fit. We have 8 data points. We should go exactly through those 8 data points. And this polyfit returns the values of the polynomial. So let's call that a. And then we print it. Print a. This doesn't tell us much yet, but we get 8 values back. A0, A1 through 8, 7. So we have 8. And that means that we can now write the polynomial as follows. It's going to be 8 a0 times x to the power 7 plus a1 times x to the power 6, and then all the way to the end, plus dot 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 plus a0 times x to the power 0, which is 0. So it looks something like this. A0 times x to the power 7 all the way to A0. But we don't really want to have to write that function. And we don't have to because there is a function already programmed for you. It's called polyval. We type polyval. And we open the parentheses. See what it asks for is those parameters of the polynomial, which we called a, and the x values where we want to calculate the polynomial. So let's first make some x values. Say our x runs here from 0 to 20. So xp, new values, is linspace from 0 to 20 and say 100 points. And then we want to calculate at those 100 points what this polynomial fit through the data is. So we do polyval and we had to give it, let me see, we had to give it the parameters of the polynomial, which we called a in the cell above, and then the x values where we want to calculate the polynomial, which you called xp. Once we have that, we can plot xp versus yp, and let's make them red. And let's also plot on the same graph x versus y, which is our data, and let's make those blue dots. And you see, it worked. We get a polynomial that goes exactly through those data points. But yeah, it doesn't look very good because it does this strange up and down wiggling through the data. And that's very characteristic if you fit a high order polynomial through data. It's forced to go through the data, but it doesn't quite work. So what we could do is go back here and say, I don't want to have a 7th order polynomial, but maybe a 3rd order polynomial. If you have a 3rd order polynomial, obviously we cannot go exactly through the data because a 3rd order polynomial only has 4 coefficients and we have 8 data points to go through. So what polyfit does, it tries to go through the data points as well as it can, and it does it in the least square sense. And with that I mean that if you take the difference between the polynomial fit and the data, you calculate all the differences, you square them and sum them up, that value is minimized. So you get the best fit in a least square sense. We run this first cell again. Now we only get 4 values of a because it's a third order polynomial. So this function really is a0 times x to the power 3 times a1 x to the power 2. And now we could actually write the last ones out too, plus a2 times x to the power 1 plus this should then be a3. In the previous slide, this last a should have been a7, where I typed a0. So this is what the polynomial will look like. We evaluate it again on our 100 data points, 100 x points between 0 and 20. We run it, and look, we get a much better fit through that data. Doesn't fit exactly, but we knew that. It fits as best as it can in the least square sense. And that's how you fit a polynomial through data. Now, if you fit a polynomial through data, it's often much better if you have a physical reason or some other reason why you think it's going to be the polynomial of a certain degree. And that's what we'll do in the notebook this week. The second topic of today is how to use fsolve to find the zero of a function. What I'm showing you here is the function f of x, which is e to the power minus alpha x plus e to the power beta times x minus x0. And for values of alpha of 0.1, beta of 0.05, and x0 of 40, I get this curve when x goes from 0 to 40. What I want to know is what the minimum value of f of x is. How do we find the minimum value of a function? We take the derivative and we set it to 0. That's what we do in the next line. df dx, I already did it for you, is minus alpha times e to the power minus alpha x plus beta times e to the power beta x minus x0. To find the zero of this function, we have to program that function. So let's do that next. I call this function mark. I like that as a name. So let's call the next function dmark dx. It's the derivative of mark. Picking good names for your function really helps. Don't just call it func. And I know mark is kind of a silly name if your name isn't mark. But if you program the stream function, call it psi. Or if you program the pressure, call it pressure. Dmark dx, it takes as input arguments x, alpha, beta, and x0. Right, here's our function, colon, enter, and then we calculate df dx, return minus alpha times x of minus alpha times x plus beta times x of beta times x minus x0. One more parenthesis. That should do it. There's our df dx. We take x to be lin space from 0 to 40 with 100 points. Y is equal to, well, maybe not x, let's call it xp, right? For x prime, or the derivative that we want to have. So we have x and y stored differently for the function and for its derivative. Yp is dmark dx at these xp values, and our alpha was 0.1, our beta was 0.05, and our x0 was 40. And let's plot it. xp, yp, red line. There's our function. And I can just about get these two functions on the same screen. You see here, this is the derivative here. The blue line is negative until about 15, 16, 17 something, where the 0, that's about right here, and then it keeps increasing. Now I want to find this 0, the 0 of the derivative. And I know, if you're good at algebra, you take a pen and a piece of paper and you can probably figure it out for this function. But let's pretend we cannot, or we're too lazy, and we want to use some kind of function to do that. For that, we have a function called fsolve. Fsolve is available in a package that is not automatically loaded by IPython. And the package is called scipy for scientific Python, and then the subpackage optimize. The syntax to import fsolve is from scipy.optimize import fsolve. Now we've imported fsolve. Let's type fsolve, open parenthesis, and let's see what help we get. What it takes, it finds the roots of a function. It takes func, which is the name of the function we want to optimize. In our case, that's called dmarkdx, I think. Right? This is the function we want to find the 0 of. Then the next thing is x0. x0 is the starting point where it starts to search for 0. And the closer you get to the 0, the more chance you have that fsolve finds it. So let's start at 10, but in this case you can also start at 0. And then it has a bunch of additional keyword arguments that you can specify. One thing we need to specify, specify args. Why? Well, fsolve is going to call whatever func you specify, and the function we specify is dmarkdx. It will try to call that function with x, the value where it tries to find the function to be 0, but it needs to specify 3 more arguments, alpha, beta, and x0. Those additional arguments you specify with the args keyword. All right, let's try it. fsolve. We give it the function name, dmarkdx. We give it the starting value for the search, say x is equal to 10. And we give it the additional arguments it needs. Args is equal to, and then between parentheses, the 3 arguments, the alpha value, which was 0.1, the beta value, which was 0.05, and x0 value, which was 40. Then we close the parenthesis, we hit Shift Enter, and it tells us 17.9543 and so on. So apparently that is the x value where fsolve claims dmarkdx is very close to 0. Let's store that, and let's call it x0 is equal to, that's our x0 now. And to check whether it worked, let's calculate dmarkdx at our x0 value that we just calculated, but also at the alpha of 0.1, the beta at 0.05, and the x0 40, and see what we get. We do get 0, so that looks like it's good. Then we can also find out what the minimum value was of our function mark at this x0. x0, alpha was 0.1, beta was 0.05, and x0 was 40. And that value is 0.49816, and that should be then about here. Now right now in IPython you cannot really zoom into this graph. That's capability that will be added in the very near future, but not in time for class. So for now we're just going to have to look at this, maybe change the x limits and the y limits to zoom in if you want to. That's all for today. I hope to see you next time.